Good morning, everybody. Welcome to SOS webinar. Today's topic is Internet of Things by one chip, and presenter is Joachim from Wiznet. At the beginning, let me say some short instruction regarding this webinar. First of all, this webinar is recorded, so whole video can be found at SOS webpage next week. Also, I would like to ask you if you have any question regarding the WebEx and so, please address this question to chat window to admin. And if there is any question regarding the presentation and you need to address this question to Joachim, please write this question to Q&A window. And during the webinar, Joachim will answer this question. Also, I would like to ask you at the end of this webinar, there is a short survey. If you can please fulfill the survey and provide us with your feedback regarding the webinar, we will be really thankful. And some of you can win a module from Wiznet for fulfilling this survey. So that's everything from my side, and I will pass the word to Joachim to start his presentation. So good morning, Joachim. Can we hear each other?
I hope so. Yes.
Yes.
Hello, I'm Joachim from Wiznet, and I hope you all can clearly understand me.
Okay, I can hear you perfectly, so so you can start share your presentation.
I don't know. I'm already online.
Yes, you can start sharing. You have the right to share right now.
Ah, okay. Yeah, just a second. This needs to change from.
Okay, now we can see the presentation.
Yes, I start the presentation from the beginning. Ah, this is the problem. Sorry. So, yeah. First of all, I'd like to introduce myself. I'm Joachim from the company Wiznet Europe GmbH. We are the subsidiary of the South Korean company Wiznet Incorporated or Wiznet Limited. And this presentation will be about our company, our technology, and our products, and later a closer look to the most important or most interesting products we recently released. First of all, I want to give you the information where you can find us the most easy way. That is our website, Wiznet in Korean, the American and the European internet presentation of our company and products. You'll find data sheets, application notes, source codes, all these informations on our company website, and more communication and other documents and supporting tools you can find in our forum to communicate questions and answers and help each other in terms of technical issues. And we have our wiki, where we have some kind of living data sheet, I would say. We can and we do regular updates, many informations here. I will show you these pages later in my live demo part. So what we will have today is a short company overview of Wiznet about our core technology we invented and we produce all our products around. Short overview about our chips, modules, special application serial to Ethernet. I'd like to introduce first here, and a short look into our Wi-Fi modules. We have a break and question and answers. I estimate this will be 20 to 30 minutes. And then we go into the W5500 chip and evaluation board, some live demo and how to do the coding, how to use it. I will show you. Then we can do another question and answer. And then I go back to that serial to Ethernet. Here we have a new module based on that chip, this 550S2E, means serial to Ethernet. And we will have also a live demo of that and some question and answer. Overall, I think this is 1 hour, maybe 80 minutes. I hope you have a lot of questions, and I can give you a perfect introduction into our company and products and technology here. Before I go into the next pages, I want to switch shortly to another presentation view. Later, we will have a look into these serial to Ethernet modules. And why are we meeting here in this webinar is because we are all thinking about connecting things to the internet. This is just a picture of a simple application, battery powered, a measurement application, humidity and temperature, you know all these. And some of these applications have a serial interface. So how to connect any kind of such device to the internet? That is the question of today's presentation. And you can do that by attaching to the serial interface, but you can also go directly to the microcontroller. You have all these options, and we will have a look into these options later. So, back to this presentation. The internet world with solutions by us and Wiznet. We have everything now with microcontrollers inside. A lot of, or most applications we are surrounded by are driven by small computers inside, like washing machine, refrigerators, television, all our home automation, and we have robots, we have factory automation, we have payment terminal, we have mobile phones, so everything is in some way computerized, and all of us, we dream of remote control by internet. And on the other side, there is Wiznet, and we are a semiconductor company, so we do all these chips, modules, and Wi-Fi solutions to connect everything to the internet. So what we are a solution provider to connect or to provide internet for everything, we would say. So that is what we are going to, and you can imagine that you cannot implement in every of these applications a computer like the one you're sitting in front of. Computers, the big computers we are used to work with are too power consuming, too big, and we need embedded solutions. So we'll talk about low power and very small microcontrollers that need to be connected to the internet in some way. Wiznet. We started in 1998. The Wiznet Incorporated was founded in South Korea. As our CEO is a Korean man, but living half of his life in America, we immediately started subsidiary in America. And in 2001, we released our first chip, the 3100. That was our first and only product in these early years. It was quite successful already. Became Inventor of the Year award, and by 2004 we became profitable. We reached a point of return so that we could invest money into new products and invented the second generation of our chips. To expand into the global market, we founded the Hong Kong branch office in 2008, invented more chips, opened the Beijing office, we invented more chips, we opened the European branch office in 2011, so that's where I'm sitting here now. And therefore we have now the European website that is much faster, so you have real-time access to all our documents, and more chips invented. And this is our latest chip, 3-in-1 solution I will explain later. Also very high-speed SPI interface, a very small, very price-effective internet interface. And we did a design contest. We named that Connect the Magic with this chip and the module. And just this month we released the latest serial to Ethernet module based on this new chip. We named that WIS550 S2E, serial to Ethernet. And to help design engineers using the chip, we have not only a plug-in module but also EBB. Growing very strongly in the last 5-7 years, we could invest money into new chips and modules, and because Internet of Things is becoming more and more popular, Internet-attached applications, we think that this growth will be very strong. And you're sitting here and you are interested in these chips because you're in some way also working on applications for the Internet of Things. This is the total overview of our products. There are 20 more modules for that, but these are all our chips, and we have many modules related on these chips. In the presentation, the first part, I want to focus on these two chips here. So what you can see is we integrated the TCPIP protocol and the MAC layer for Ethernet. We added the physical layer, so we have the 3-in-1 chip family, also including the Ethernet PHY. Means you can connect RJ45 MAC jack directly to that chip. And in some of our chips, we integrated the MCU. So we have 4-in-1 chips with MCU, TCPIP, MAC, and PHY. And these 3-in-1 and 4-in-1 chips are the key to enable small microcontrollers. As you can see here, there is only an 8051 core or a small Cortex M3 or M0 or whatever. You can add that and attach that to the Internet very simple and very easy because TCPIP is involved. And that's the key technology I want to introduce to you. So in your computer you're sitting in front of, you have the MAC and PHY on your network card. That is attached to the system bus, PCI, PCI Express, whatever. And on top of that, everything else is operating system and software. So the controller on your PC, even if it's a quad core or whatever, need to process all internet traffic and protocol in software in the main processor. And looking at that, we decided in the early 90s, so more than 20 years ago, we took a closer look into that and thought about how could it be possible to give internet access to small microcontrollers that are not able to process all this data in in an appropriate time. And below this here is timing critical. If there is some data coming, you have to respond on these layers in a sophisticated way. The approach was to analyze the TCP and UDP protocol, the IP Internet protocol, and all related packages and handshakings, and implement that into pure gate logic. And this approach was successful by the late 90s and implemented into real silicon by 2001, so that we have a simple hardware TCP IP Internet Ethernet gateway chip. And that is our core technology. And because this is all silicon gate logic, you have response time and traffic into the internet with always the same high speed on this level, and the data throughput is only related on your system on top, where you have to provide the data or you can receive the data. And the faster you can process or generate data, you can transfer it. The bottleneck is not longer the core speed processing this. The bottleneck is providing data and analyzing the pure and real raw data. And this is what you gain in performance. This is on a 200 megahertz ARM9 with a very small reduced embedded Linux operating system. We used to analyze the load on the MCU and the speed on the internet. And as you can see, if we do not start any other process, just send and receive data in the internet, and you have a standard embedded Linux TCPIP software implementation, you gain a maximum throughput of 30 to 40 megabit per second. If your microcontroller has to do any other task like measurement, data analysis, or whatever, doing your application, that is the purpose of your application, doing something, then the speed on the internet is dramatically going down. But why do we occupy the controller only to process TCP/IP data? If we offload all these TCP into hardware, we get all these resources free. It's only mainly doing buffer management and copy and paste data into our chip. And then all of a sudden, on the exactly same MCU, on the exactly same PCB, just by exchanging the software TCP/IP driver in the Linux operating system by enabling the hardware TCP/IP, the line speed is independent of the MCU processing load. Even if you start multiple processes, the speed of the internet is still the same. You only have to do the mem copy. So the other way around, you don't need this 200 megahertz ARM9 or nowadays an A8 or whatever, a mobile phone usable MCU. You can use a small 8-bit MCU and you can do a perfect internet application. So we have a closer look to that. How is internet working? What is the TCP/IP protocol all about? TCP/IP is mostly like doing a telephone call. There is a client and a server structure. So the one in front of the telephone I name server, and the one picking up and initialization of the process is a client. So we take a look on the server side, and if you init a TCP IP connection, you prepare your telephone, you switch it on, and then you're sitting in front of it and waiting a call to come, and you listen. So the status of the TCP core is moving from close to listen. And then if a call is coming, the telephone is ringing, it's a SYN packet coming, and you have to answer this SYN packet by saying, press the green button and say hello, who is calling me? And then the other side will say, yeah, I'm your friend and I want to chat with you, do you have time? And then you will acknowledge that, yes, I'd like to talk to you, and then your connection, your telephone call is established. And that's all what is happening. So you need to go into a listen status, and you have to respond to an incoming call. And all this is timing critical. You have to do it in a certain time, yeah, because the other one would hang up if you're not responding immediately or after 2 or 3 ringings. So we have the same here. If we do not acknowledge this SYN packet, so the ringing will be repeated 8 times, and then the connection will be refused. So it's very similar to a telephone call, but this is all done by the hardware engine here now and is not disturbing your controller. There will be no interrupt, nothing, because this is all processed in hardware and the close process as well. So if you close a connection, there is also handshaking, and all these handshaking need to form the packaging, need to make a checksum, and a lot of processing is needed to do that. And we put all this in silicon gate logic. So if the connection is established, you can just exchange data, send and receive data, and every time a data packet is received, there is an acknowledge, and also this acknowledge is formed automatically by our engine. Even more, your raw data, like here the DATA, this 4 byte, for example, need to be packed into a TCP packet, need to be packed into an IP packet, need to be packed in a MAC layer packet, and then into the physical layer in those ones and zeros on the Ethernet line. And all these packaging is done by our hardware. So you only have to transfer these 4 bytes into our chip and tell our chip, please answer into this established connection, and then these 4 bytes will be automatically packed into a appropriate TCP package and sent, and you will receive the acknowledged status and can check by your microcontroller this status. In approximately 30 minutes, we are in the other presentation, and I can show you exactly where this is happening and how this is happening. By now, I leave you with this. Just have the information that this is how TCP/IP is working. And to give you a more detailed view on our chips and core technology, I have here our 4-in-1 chip, the W7100A. This is the complete block diagram, and give you the information that this hardwired TCP/IP core, we are the world only and world first semiconductor company providing such an silicon-based TCP implementation for the embedded world. And this gives you the performance boost I talked about, offloading those processing from your host MCU. This makes the application very stable and very simple. You can use a very small core and only a few lines of C code using this like UART serial interface or like like SPI engine, I2C engine, or like USB interface. So this is all you need. And you can use that without any operating system, without any interrupt, but you can also use it with operating systems. We provide Linux drivers and open source codes to support many applications and many different MCUs. In 2001, we implemented first this 2-in-1 technology, 2-in-1 chip, so the TCPIP core, supported by memory, by buffer memory, and including the MAC layer, and a standard interface to any external physical layer PHY or switch chips. So that is the media independent interface we have here, and we still will also in the future provide chips in this 2-in-1 family. Most interesting is, of course, having the physical layer also in the same chip. We named as 3-in-1. So you have a complete internet interface in one silicon chip. On top here you have SPI 8 or 16-bit parallel interface. You have the TCP core. By the way, this is existing 8 times in parallel. If someone of you have maybe thinking about how many connections can I handle at the same time, a PC can only handle one connection at one time and has to switch from one connection to the other connection in an interrupt state machine multi-threading mechanism. Here we have 8 of these TCP cores parallel. So that means in such a telephone call scenario, you have 8 telephones in front of you, exactly the same time and all in parallel. And you can talk to all these 8 connections at the same time, even with the smallest microcontroller. Because the connection management is completely parallel. And to support all these 8 connections, we have a big dual ported memory here, so that all these 8 connections can send and receive data at the same time. Dual ported means that you can read and write from 2 sides into the same memory at the same time. So even if our core sends some data, reading it out from this memory into the internet, your microcontroller can do at the same time access to a different part of this memory and write new data into it. This is a very powerful part of our core technology. Of course, such a chip is supported by clock generation and distribution all over. Internally, we use clocks up to 150 megahertz, but externally we use only small frequencies. And for the physical layer, we need the 25 megahertz. Internally, we use also different voltages, like 1.8 volt, but you source our chips only with a single voltage of 3.3 volt. And in this 4-in-1 family, we also implemented a microcontroller. And that microcontroller is, of course, supported by flash memory and supported by RAM. So now you have an overview of our chips, the 2-in-1, 3-in-1, and 4-in-1 chips. I can give you a different point of view like this. So you have the 2-in-1 chip with Hardwired TCP, IP, and MAC. That's the host interface to your most loved MCU with a high-speed SPI interface or 8-bit direct and indirect means with or without an address bus. And In the 16, oh, wait, it's not written here. 16-bit interface, this is 16-bit interface. We can also provide a direct memory access mechanism. So MCU can directly access into the buffer management without MCU load. With implementing the physical layer inside, you will see the chip become 3-in-1. And later I will show you much more details of the 5500 chip with its high-speed SPI interface. But back to the 2-in-1. The MII interface is very useful to have external physical layer chips or even a switch with multiple Ethernet connections. The MII interface is a synchronous parallel interface. Means that here is a parallel interface clock synchron to a clock signal, and it's very high speed. It's a 25 megahertz or even a 50 megahertz. And so the PCB layout on this MII interface needs to be well done. It's very flexible because you can use different type of PHYs and switches, but it has some more signals. It's 4+4 parallel, so 8 signals in the parallel interface plus 4 or 5 handshake lines, so you have 13 wires on the MII interface. And if you have the physical layer inside, you only have to connect the magnet and the connector. And that is a very simple and easy to make attachment here. And so with that chip, you can easily add any kind of Ethernet connectivity to your MCU. And in the 4-in-1 family, we have this one silicon-made 8451 core plus Internet interface, and we did 2 die in one package SIP with an STM ST microcontroller. That is the 7.2. We might have or will have more controllers in the future, but by now this is our portfolio and the chips we can offer you and we recommend to use. Yeah, this is the same product portfolio in an overview. I think this is more interesting if you review the presentation by your own. You have a small comparison of all these chips. And what you can see here already, but this is half secret or still, by the end of this year, we will have another Cortex M0 added with the 5.5 technology, but in one silicon. So this is not a 2-chip, but a single chip like this one. Yes, so with all these chips, we build plug-in modules like this. So you can easily use this chip with your MCU or your evaluation board or your application. Here you have the SPI interface with this module, but we have also the modules with 8 and 16-bit interface, more bigger shape. And we have serial to Ethernet gateway modules like this one, and also as a chip solution, our pre-programmed microcontroller with the serial to Ethernet application I will show you. And we're supporting 1 serial port, 2 serial port, 4 serial port connecting to the internet. And you can see already we have Wi-Fi modules. We're providing client modules as well as access point modules. We have some external device, or let's say these are applications like you doing implementing wired or wireless technology um, into full application products. Just before the break, I like to go into slightly more details about these products, just a few more pages, and then we will have a short break with some question and answers. I think you have maybe a lot of questions. So what we name plug-in or I/O module is just our chip added with a NAC jack, so you can use that more easy in the development process. Here you can see a lot of pins, that is 16-bit interface. Here you have an 8-bit parallel interface, and with the small modules you have the SPI interface. And so you can use our chip just within a few minutes with your microcontroller or with any kind of evaluation board from an MCU vendor by using and plug in those modules into your MCU board. As you can see, we have here one module that fits perfectly into a microchip development board. You might know the Explorer 16 from microchip that has this interface, and you can plug it in and you have an internet interface with your microchip. But we are totally independent from microchip. We support any kind of MCU. I show you later. And this is same again, more detailed view of this module. We have the 5.5, this module and this module using the 5.2, and gives you the SPI 8 and 16-bit interface to the Ethernet. Using our chip together with an MCU, we can create any kind of application, and we use that to create serial to Ethernet or serial to Internet applications, S2E modules. The MCU offer an interface with a TTL level, voltage level of serial interface, or added transceiver for RS-232, RS-422, or RS-485, and up to 4 of these serial interfaces with different pin outs or even a DB0 connector. And on the other side, we have the Ethernet connection. And as we did the 4-in-1 chip also, we can also use a single chip solution for that kind of applications. So have a look into the one connection modules. That is the WIS 100, 107, 110, and latest we break a little bit the naming rule, the WIS 550 S2E, and this is the TTL level module. And these modules provide you one serial interface, like you can see here, one serial interface, and to the internet. Then we have modules like this, providing you 2 serial interfaces. And we have modules like this providing 4 serial interface. And now I want to show you that we are using Core River MCU, NXP MCU. We have our own internal 8051 here, and we are using ST Micro. On other modules, we use Atmel, and we are supporting also TI, Renesas, Microchip, and many other MCU core and MCU vendors. We are totally independent of MCU manufacturers. So that's only because of different purposes. Here, very lot of interface, we need a bigger MCU. With only one interface, we can use a small MCU. We choose the most and best fitting MCU for application purpose. Here, for example, the NXP Cortex-M0 has an integrated E2 PROM and is a very small and cheap MCU. So we have a very strong and reliable serial to Ethernet application. Maybe one important information missing: all our modules are also industrial temperature grade certified and tested, and in a high volume mass production in South Korea. So they are not some unknown Chinese production modules that might change in a few weeks and months and be not available anymore. These modules are available. Some of these modules, like this one, is available now for more than 5 years. And we provide these modules industrial graded for at least 5 years and hopefully more than 10 years. So we are aware of the demand, of your demand, to have access and constant supply to the same quality and same product over many, many, many years. And we will not obsolete modules or chips without an appropriate notice. So you can use all these modules in an industrial application and in critical applications. Okay, then we also provide these serial to Ethernet application we did for the 107 module. 108 is one for the 422.4.8.5 interface. We did this application in this single chip, and we provide it pre-programmed in a QFP100 or in the QFN64 pin package. If your application is small or cost sensitive and you don't want to touch your application, you have a serial interface and you like to integrate Internet interface and Ethernet interface, you can use this chip as a bridge between your UART interface of your application and the Internet. So we're providing not only a serial to Ethernet module solution, but we're providing also a serial to Internet chip solution. The only thing you have to integrate is the two crystals, the application crystal and the physical layer crystal, and from your MCU side, clear reset the 3.3 power supply and the serial interface. So it's quite simple to use chip serial to Internet. This is the overview. Here you find again this chip, and here you find all these modules with TTL level, RS-232 or 485, with pin headers or DB9 connector, with and without the MAC jack, with and without power regulator. So there is a variety of modules available. I'd like to give you a short overview over the Wi-Fi modules, and then we do the question and answers. As we are the wizards of Internet, Internet is not only Ethernet, is not only wired Ethernet connectivity with an RJ45 and the cable, but Internet is also Wi-Fi. And we are very strong in doing Internet applications for many, many, many years. So it's logical that we are also active in the wireless Internet connectivity. And we are providing a Wi-Fi 200 family of modules for client applications mostly. So that is serial to Wi-Fi with integrated TCPIP stack and everything, Wi-Fi stack. So you can easily plug these modules to your MCU using like our chip. And we have also embedded modules for the access point side of an application. One module giving you an MII interface as Ethernet, and this module gave you multiple Ethernet interface. What you can see immediately is that a client module is able to do low power because it does not have to be always on. It can be shut down, it can go into sleep modes, while an access point repeater router application is always on, need to be always receiving and transmitting data, so this is more power consuming. Let's have a closer look, just 2 more pages. The 200 family modules we provide with a UFL connector, with a chip antenna, or as you can see here with a pattern antenna. Here we have also antenna diversity, so the module decide whether to use the connector or this PCB antenna. And we provide also 50 ohm antenna signal here on the corner, so that you can use any kind of external antenna. And most interesting, in client applications, they can go into sleep mode for, let's say, 10 minutes, collecting data with your microcontroller. Then you activate the interface, and that is going very, very, very fast. With a few milliseconds, you're online on your access point, can transmit data, and then you go into standby and sleep for the next 10 minutes, for example. If you do so, such an application can be battery powered for many years. So we are able to provide wireless internet connectivity, even battery powered. And the point of view on the access point, we can see this module provide you a full functional router as you might have at home, multiple Ethernet interfaces, even a USB interface and serial interface, some status and general purpose IOs. This module, this 5630, comes with a mini PCI Express interface footprint connector, but the signal is of course very special. You have that 3 Ethernet interface, you have the LED signals here, you have the UART and the power supplies. And such an access point module can do multiple things. It can be the access point for the local network, just connecting the local network with each other. There is an option to provide a dynamic IP address. It can be client and connect itself to an access point as a client from this side, but with network address translation provide access to the internet, for example, to a local network. If you combine the access point and the client, you can do something like this, so that multiple devices can connect to this as an access point, as well as our module as a client connect itself to a higher level access point. So it's a combination of being access point for the local network, as well as being a client to a different access point and have the internet connection. You can reduce this just to be a bridge, and it can be gateway with providing IP address to the local network and to as a gateway the internet connection. Then you have direct internet connection here, not an infrastructure router here, but this is the infrastructure with the network address translation. All these functions are provided with our module. Okay, that was a very fast total overview of what we offer to you, and with our core technology of hardwired TCP/IP, we give you the possibility to have internet applications without any operating system, with high speed, only one chip needed, with a very low price, and I hope we can provide you good support. You can use that with any MCU, as we are independent, and this gives you a very robust, a very stable, and very secure internet application. Just added the information that we are a Korean company, have approximately 30 and growing people, more people in Korea. Our Korean headquarter team is also responsible for our Japanese business. So we have the headquarter and we have our Japan team in Korea. We have the American subsidiary. Oops, this is the wrong. We have the American team located in Silicon Valley. We have the Hong Kong and Beijing team, and we have the European team. I'm Joachim, and I'm supported, and we are equal with engineers Tobias, Felix, and Sonja, and our head management is Mr. Geun-Hong Lee. He is running this branch office. Okay, thanks. Here again, more contact data, and we can go into the questions.
Okay. Yes, we have some questions, so I start with the first one, and the first question is, which is the best UART bound rate for Wi-Fi 250?
Okay.
I will let's continue on this question.
This is related to the Wi-Fi. That's okay. No. Those serial to Wi-Fi modules provide the UART interface as well as SPI interface, and the UART interface with 210/220 is I think the 230K, and the Wi-Fi 250 is providing 1.9 megabit per second on the UART. So you can yeah, this is really a high-speed UART interface. And on SPI, those modules can go in the range of 3 to 5 megahertz, so even faster.
Okay.
I think we have to add that here somewhere. Yeah, maybe we can. I'm not sure about here. I think it's 230K. Maybe I have to check that. It's already the 920 or 930, but I'm not 100% sure. Same here. And here we are. I'm sure we provide 1.9 mega. 1.63. Yeah. On the serial interface. Yeah. Mm-hmm. Mm-hmm. Yeah. This. Okay. Mm-hmm.
Okay. Can I continue with the question?
Yes.
Okay. This question continue. The datasheet states 36, 86, 40 and 18, 43, 20, but I assume that the MCU inside Wi-Fi 250 is not clocked in multiples of 300. Should 2 million, 4 million, 6 million, 8 million work better? Have you tested?
Tobias, did you understand that question? I'm a little bit confused.
This question is also written in Q&A window, so you can read the first one.
Maybe I have to check. Where is the Q&A?
It's the first one.
Ah, I couldn't see that window all the time. Yeah, the first one. The UART baud rate.
On the top.
Yes, yes. Do you see that? If not, come around. Okay, Tobias is coming to my desktop and we'll have a look at that question. So it's about the data rate, not multiple of 300. Yeah, we have to ask or forward this question to our department, for our engineers in Korea. But I can say like this. Inside the Wi-Fi 250, we have a Cortex M3 standard MCU. So the UART interface is provided by a standard MCU vendor, and is nothing very special. So it should be UART as many other known MCUs have the UART interface. But anyway, can you, Mr. Lars Rockstone, you can forward this question?
Okay, I will.
Yeah.
I will copy this question to you, Joachim, and give Mr. Lars a copy of this email so you can directly answer to the mail. Okay. The other question is, what does the SPI protocol of Wi-Fi 250 look like? Does it use 80 commands like UART?
Yeah.
Would you refer to a place in the datasheet where I can look it up?
It's in our wiki. This all is in our wiki. Wait a sec. This is very simple. Where is my... If you go into the wiki, that is thiswiki.net, wiki, that's the Wiznet wiki. Also from our Wiznet website you find the wiki here. So it's wiznet.eu and you go to this wiki. And that's the forum. And here we have the wiki again. And here we have the Wi-Fi 250 in our wiki. And here you have the programmer's guide. And in programmer's guide you have the AT command set. And here every command is explained. Also a lot of here every single command is explained. And we have application explanations here. A lot of and all these information should be found here. If not, there are more possibilities. You can go into the forum, of course, and ask questions about the Wi-Fi 250, for example, here in our Wi-Fi module section in our forum. It's thiswiki.net forum, or so you can check here if you can find the answers. And of course, all the time we are always available by support. Here by our email address support. And the application engineers of SOS Electronics also know about the Wi-Fi 250. So you will be supported by SOS also.
Okay, thank you for your answer. May I go for other question? So other question is, next question is, how much is the CPU load on the Wi-Fi 250? Is UART or SPI the bottleneck of the Wi-Fi 250?
I would not say it's the bottleneck, but of course the SPI and the UART have a maximum speed, and that's the speed of data transfer. So the internal MCU can process the data fast enough the data is transferred with the speed of the interface. So yes, the interface is the bottleneck.
Okay, thank you. The next question is, does Wiznet Europe compile a firmware?
Yes, but by now, not for the Wi-Fi 250. I have all the resources. I have the tool chain here. I have the source codes here. But it's a very complex application, and our resources here in our Europe branch office are limited. And if any kind of customization of the firmware is needed, I forward this to my Korean engineers. So they will do that, and we can cooperate with the customer. So I can do I'm the man in the middle, transferring the customer demand to the headquarter engineers, and we can negotiate terms how to do that.
Okay, thank you. The next question is it possible to use GPIOS on Wi-Fi TCP as a data signal configurable by AT commands? And in this question are examples. For example, URTX 0.
Yes, the idea is to not only to transfer data from serial to internet and back, but also to control some GPIO pins of the module. And yes, that is possible, but it's not yet implemented in such a straightforward way. So I think this is something we can maybe negotiate with some customers. Maybe your customer here can contact us, and then we can implement that straightforward. But I think in some kind of demo, it's already working. Yes, we can control 8 general purpose I/O pins.
Okay, thank you. The next question is, can I use Wi-Fi 250 with UFL and external antenna for diversity?
Yes.
Okay. The other question is network modules versus serial Ethernet modules. Do you know some typical application examples for each group, advantages?
Yes, I think that is something very interesting for all of our audience here. I will go back to my overview here. So if we talk about a serial to Ethernet interface or solution, whatever, we have here a serial interface from an MCU, and we have down here the Ethernet interface. That could be wired, but could be also wireless. The advantage is that you do not have to care about all these. The application inside the MCU is from us, and we provide some AT command, and you just use some AT commands. And this application is totally invisible, transparent. So data put into the serial interface is transferred exactly as from here into here. So it's a pure gateway, just transferring data from this side to this side, and some AT commands or serial commands used to configure and to control it. The disadvantage might be the speed. As we said, this is the interface here is a UART interface, and this has a speed limit, and also it's not that flexible, let's say it this way. So you have only these transparent data channel, and you can connect to systems that are able to be connected by the firmware. I can show you immediately with the next part of our presentation. Therefore, if you have an application where you have your own MCU and you code your own application, then
ask the next question. Okay.
I want to show you. So to access here, by SPI or 8-bit, using the interface as an interface, you are much more flexible, and the speed here could be up to 80 megabits. So it's the full speed the MCU can provide. And then you can do every kind of application. You have those 8 connections and you can do everything. So that is the difference.
Okay, may I ask the other question?
Yeah, there is one about the IP6 support, right?
Yes, hello. For IoT, it's important IPv6 support. Can you tell more, summarize this topic?
Yes. We did the IP6 already in hardware. It's working. IP6 is working in hardware, but we did not release any kind of chip yet because our first chip was not working good enough to be implemented in our customers' applications. We address industrial applications, and such a core and the chip itself must be very, very stable. So we will approach again by end of next year. We are working on the chip, on the next generation of IP6 chips, and as our core is already proven to be stable, I'm sure we will be successful and the IP6 chip will be released end of next year. And to add just the next question, all our chips, where is the overview? All our chips here, these chips, some are already 5 years or even 6, 7 years old, but we guarantee in a written statement these chips are minimum available for the next 5 years, and our plan is to have them available for more than 10 years. So, for example, if you start now an application here with the 5.1, 5.2, 5.5, 5.3, whatever, from today on, we guarantee you in a written statement that it will be available 5 years minimum. And if we are forced to obsolete a chip, then this is forced by external forces, not by us. And then we will give you a 1-year period where you can order as many chips as you want, and we can even store them and provide you for the next years. So there will be a procedure of a last time buy, an end of life announcement, so you will not get lost from one day to the other. And yes, the 5.1 and the 5.2 will be available for the next 5 or even 10 years.
Okay, thank you. So so far there were all the questions answered. So we can continue.
Yes, I have to accelerate a little bit. We have already exceeded the 1 hour. I want to give you a short introduction into how to program our chip and use the serial module. I think we did already a lot of information, so I can accelerate here much more quick. So I introduced this hardware approach that we have the TCPIP in hardware. Have a look at the 5500 chip now. We reduced this chip to the minimum. So we throw out the 8 and 16-bit interface. We have only SPI interface left. We shrink this to the latest semiconductor size. So the 5500 is state-of-the-art silicon. It's very power efficient, and because a small chip is cheap, this is also very cost effective compared to old chips. And okay, this information is the same as before. I just want to repeat and give you this information again, that we have 8 of the TCP/IP connections at the same time. Every ping package, every ARP package is automatically processed here and answered. So if there is some broadcast packages coming along in the network, it's coming up here, answered or dropped, and there is no interrupt and no disturbance on the application also. That's the main and the most interesting feature in having a hardwired TCP/IP core. And on the second point, we have this external memory here, a dual ported buffer, and with 32K bytes, it's enough to support all the 8 channels at the same time. And this is separated memory from MCU memory. So from MCU point of view, our chip is like an external memory and only a data memory. It's not for there is no code inside or something. So this gives a very stable, a very reliable, a very secure internet interface. Yeah, I think we got that. This is the performance again, and this is how it works with this telephone call, init and sync and acknowledge here. And we go into the source code slightly to have a look how is that used. And what you can see here on this page from here to here is a complete TCP/IP answering machine. I named it web server, it's a TCP server, so it's only this 20 lines of C code that process everything. We start with an initialization, but then in this while loop, we constantly check the status of this connection, whether we are here, 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 or here. And then we have the case SOC established, then we can transfer data. If the socket is closed, we reinitialize it. So we go from close to init to listen. And if we are in listen mode, we don't have to do anything. We just wait that something happens. Any client is connecting, then our engine is jumping into the established mode, and we are here. And if so, we can simply check how many data did we receive. We can read out these data just by access to our memory. It's a mem copy from start to end to read out the data. And if you don't do that, just we receive the data, but just checking and deleting the buffer, and we send hello world back. This is a very, very simple application. But if you send here a website and you listen here on the port 80, this is a web server. So the key is to tell our engine the protocol you want to proceed, TCP, UDP, or MAC or IP, a port number and memory size, and then you have the socket in listen mode, and you can open and close, connect and disconnect. And if you are connected, you have the socket established, and you can send and receive data. This is receive data, this is send data. And behind these two commands is just a mem copy. Just copy the data into this buffer. It's just an SPI access to the buffer, read and write. And the commands to send data is here some registers that give access to a configuration and give you the commands send and receive. Okay, this is this is summary. I dropped that. It's very simple, and this is very complex. And because the TCP/IP is in hardware, and we have the separate memory, the dual ported buffer, memory. These applications rely on Wiznet are very secure. You cannot attack such an application by virus or method like that, because there is no operating system on top. Any kind of TCPIP package that is manipulated or has some code inside is only going into our memory, or even not into our memory but just dropped because it's not for our application. So there is really no way to attack the upper layer application. And if we talk about ping, ARP request, something like that, a simple denial of service attack is not possible. The silicon logic processes TCP/IP packages 200 times faster than a quad-core i7. Your PC you're sitting in front of is using an operating system that is jumping from different task to different task and needs to check every single TCP or UDP package that is coming in. And it needs to process that on the core, on one of the 5 or 8 cores you have in your PC. Here we have just a few thousand transistors in a transistor logic, a gate logic, that split up the package, analyze it, look into it, see, this is a ping or an ARP or any other low-level internet protocol, and our engine is answering directly and independent of the upper layer MCU. And this is way faster than any MCU can do that. As long as you do not attack the upper layer application, such an application is always available. It will not be down by any attack. Okay, the purpose, and we have another maybe 5 minutes or 10 minutes, is I want to show you how to use the EVB and how to use the serial to Ethernet module. I will accelerate and do that in 5 minutes. So we have an EVB that has our chip here, that has in this way here NXP Cortex M0. There's a lot of flash and memory. We have a real EEPROM inside of this MCU. That's why we choose this one. And we implemented here some temperature sensors, potentiometers, and RGB, LED, some extra flash memory if you like to use that, some buttons. And we have connectors here that are Arduino compatible, but also all other signals. And we have a 10-pin debug interface, so you can develop internet applications quite effective on this MCU, or you use our modules based on the 5.5 and add it to any other MCU. What I can show you here is a very simple loopback answering machine. So we send data from our PC to the internet, and that goes into our EVB. So the connection is from the PC into here, into our chip. And the data is just sent back, and we can see the same data coming in here. It's not a very useful application, but very simple. And my PC has IP address 28, and I gave this loopback the static IP 222, but also DHCP is possible here. It's another very simple application to make a dynamic IP address. Have a closer look to that. Yeah, give you just a short look into this application. We open the development environment from NXP. The development environment is named LPC Expresso. And we have here this EVB demo loopback, and switch blinky means we can manipulate the LED. and in the main loop, we initialize the SPI interface, we initialize the chip, we make a network configuration, and then on the serial interface we output some informations. Also we output the network configuration, and then we go into this while loop, and as explained, this while loop is a very simple loop that processes just loopback TCP. And if we go into loopback TCP, you can immediately see this switch, and then that's the same we saw before. If a socket is established, we print I'm connected and see that, and then we receive the data, we check size and everything, and then we just send that data back, the same data. And if we do so, I say on the serial interface, data is returned. Let's have a look at that. So, this is my setup currently. I have the EVD here, a USB serial connection for the debug, and this Ethernet cable goes into the switch. So we have the loopback inside our evaluation board here. Here we have the serial to Ethernet module. I can show you later, but that's also very simple. Application look like this. You have a terminal program. I clear that and I disconnect everything. So in the serial configuration, I go to my COM port. I have chosen the 115K baud. I open this connection, and if I click the reset button on my evaluation board, you can see that the evaluation board immediately answers, and it has a network configuration. You see the static IP address, and it has a UDP port opened, and it has a TCP port open. And here in the lower part, I have a second terminal for network communication. I'm a client, not a server. I'm the client here. I like to connect to that board. This board here has the 222, as we have seen here. And on port 5000, it is listening. And as soon as I connect, you can see that there is this message connected. I can see the IP address of my PC. And now I can send here some data. And it's immediately returned to my terminal, and I receive the message data returned. And I can repeat that with any kind of data, and you see it's always returned. The data is just here. So it's a very, very simple application. But imagine this is also remote control. Every time I send data, there is something happening here. I can output data on the serial interface. Maybe I can control something with that. So this is already an Internet of Things application. If I do not output data on the serial interface, but maybe switch on and off some GPIO, that might look like here. GPIO 1 on, okay, and data returned. This could be an Internet application. And as you have seen in the source codes, this is the full application. More is not needed. We can go into this receive and send commands. We established that in our so-called I/O library. It's a very simple library offering these commands, let's say this way, but behind that is more or less an SPI mem copy. So it's very, very simple. And yeah, I think I will stop here, and maybe we'll have more questions. And if you like and have more time, I can also show you how the serial to Ethernet modules are working. Because they have a configuration tool like this. So if the serial to Ethernet module is connected to the network, first I remove the connector so you can see search end up in nothing. And if I connect it to the internet, search immediately find my module, and I can configure it, and then I can use it to transfer serial data to the internet and back from internet to serial interface. I don't know if we have enough time, but maybe there are questions.
Yes, we have one question regarding the one particular problem with the application and solution. So I would like let this question at the end of webinar for your discussion directly with our participants.
Mm-hmm. Can you advise me how much time do we have?
As much as you want, but the webinar was planned for hour and a half, but we can continue.
Okay, so 90 minutes are over now. Maybe we spend another 5 minutes into the serial interface, the serial to Ethernet gateway application. That is quite simple. I connected it already. You can see I configured it. Maybe I give you a short introduction first. So the idea is you have an already made application, maybe a home automation application or a medical application or any kind of security payments or whatever related application. Many of these applications might be fixed and closed because they have a certification process, they are security critical. So changing something inside is very difficult. And then we need to access to the interface that are available. And in this here, I have that next to me in my window. This is my window. This temperature and humidity application provide me a serial interface. And I cannot reprogram that because this is from a department store. I cannot change it. So I have the Ethernet interface. And I can simply plug my module to the serial interface and have access by internet. And even this can be implemented inside some medical or security critical applications provide internal serial interface, and you as our customers, you don't want to change your application because measurement applications or security critical, you don't want to change that. You don't want to implement any extra code into the same MCU. You like to have a separate internet interface and attach it by the serial interface. And that's what we are talking here. And I think this is very strong. I will give that a big our serial to Ethernet modules are in the range of 500 milliwatt. Full application, full MCU running applications. So you don't need big energy to provide internet applications. You can attach a Raspberry Pi or any Linux board here, but that is a 5 watt and not a 0.5. And such a Linux operating computer might not be stable enough for a medical application, might not be secure enough for security or payment. But without any operating system and directly attached to the serial interface with such low power, this might be the solution you're looking for. And there are many more applications possible. Okay, I have seen that. We have this two or single microcontroller possibilities. The overview you have already. So this is our module with the TTL level. And we need 150 milliamp at 3.3 volt, the max. So that is a 495 milliwatt. And here's all you need. You have the MCU. Even this one is pre-programmable. We have here the debug interface. If you like to do anything with this module, we have some general purpose I/O pins. You can even use this. You can see here are some reserved pins. Here are not connected. That is also general purpose I/O. These status pins are general purpose I/O. We have the serial interface, TX, RX, and RTS, VTS. Even those pins are general purpose I/O. If you like, you can implement any kind of internet application even in this MCU and use this general purpose I/Os to switch on and off something and control things in the internet. This module is not the only thing we offer to you. We have adapters for RS-232, we have adapter for RS-422 and 485. That gives you the power supply, that gives you the transceivers and some buttons and switches. And we offer both bundled with this order code. You can order the WIS500 SOE232 or the 485, you got the bundle. Here we have again these adapter boards. And now in front of me I have this module attached to the same network as my computer, and on the serial interface I have also my computer, okay? And I can show you how to configure the module and how to use this as advice and how to find the information you need to know. In our wiki, we have our living data sheet and all information for this serial to Ethernet module. The firmware you can update, you can make bug fixes, you can even manipulate yourself. You can also find in the wiki. We will publish the source codes within this year. So by the end of the year, you will be able to have access to the source codes of the firmware, and you can do anything with that. Then we have a forum with questions and answers. So if you go into firmware customization, you might end up with a lot of questions, and you can exchange ideas with each other. And we are also active in the same forum, so we can support you in terms of technical questions. Also, engineers from SOS are active in the forum, so you can have the best support. Then we have the configuration tool, that is a Java application. We will release the source codes also by next month. So if the configuration tool is not appropriate to your needs, you can even implement your own company pictures and layout. Some serial terminal, this device terminal, or you can use HTerm, or you can use Arcoles by the HW group. These are the tools we used to use as engineers here at Wiznet, and we provide this linked in our wiki. And I will use this now in front here on my computer. I have my computer, use the serial interface to connect to the S2E module, and the Ethernet connected to my PC. And I see the same data in and out here. So this will be a loop. My PC has again the 28, and the module will have the 22. Okay, I can make that. And I can show you now. The config tool look like this. So what we want to do is we like to configure the module with this IP address. It should be server, for example, and we like to connect. So what first we can do is search. Then we see the module with the MAC address. This MAC address is provided by Wiznet. So the 0008 DC is Wiznet, and this one is unique for the globally. As my PC is in a network of 111, we need to make this module in the same network. What we can do is we can activate the DHCP, then the module will receive an IP address from the infrastructure. If we want to set this, we need the setting password, and I will change that immediately to 0. And also, I don't need any connection password. This is some kind of protection, but to show you quickly, this is a little bit disturbing. Now, this setup, I will configure, and then it's requested. This is Wiznet. Now it's successfully set, and if we search again, we have to wait a few seconds that the module receives the IP address from our DHCP server. I think this should be right now. We try again. Search. Not yet. Sometimes DHCP needs more time. Ah, there it is. Okay, we have the 111.158. So then we can change that. Here it's the 158 now. Okay, and we use that module as a server. So we will use our PC as a client. I have to disconnect here first. I clear that. I clear that. And if I press the reset button, I have to connect here to the serial interface. Close. This is serial interface number 7. Something wrong with my serial interface maybe. Just a sec. I have to double check my serial interface. It's one of these two. I tried the other one. This should. Wait. We are here. What was that? 158. 158. I connect here. And I send some data. Yeah, it's working here on the COM7. So now I'm here on the network side. How to do that the best way? This is not ready anymore. Back. I'm here on this Ethernet side, sending data. Sending data to Ethernet. And here we receive the same data. We are sending data to area. And I receive that on the Ethernet side. So this is fully transparent. Every byte, even only one byte, comes in here as one single byte. And we can transfer this data transparent, just in the closed loop. So you can connect to this serial interface any of your applications, and you have access by the internet in many ways. One thing I want to advise is our module can be client also. So if your computer is server, we can immediately do that. We are the server now. My computer has the IP address 11.28, right? Yes, 11.28. And I'm listening on port 5000. Here's server mode. Now I'm the server. My PC is a server on port 5000. And the module can be client. Connecting to that, I set that. Now I deleted the password. The password is empty, so I can immediately confirm that. And now the module is the client. But from this point of view, it's always the same. We send data here. We receive it here. And we send data here. And we receive it here. But this time, the direction of the connection has changed. My PC was listening, and the module opened and established the connection. So you can do both client and server with the module, depend on your setup. Even a mixed mode is possible, and UDP, but UDP is sending data without any control. Could be useful. So many more options existing. Like we have a command mode. So if I go to the serial interface, and this is not good. 3.1 is a 1.1.1. I set that. If I enter 1.1.1, that is the hex 3.1.3.1.0, I'm now in a command mode, and I can send commands. Should work. Just a second. Okay, you have to check, maybe I have to check the wiki again. Here is explained. Where is the wiki? Here is the wiki. S2E module. It has this programming guide that also the module can be configured by an AT command set that look like this, so that you can configure the module from the serial side, and this is controlled by an enable sequence, and this sequence is then 3 digits, like my 1.1.1 here. I'm not. Now it's responding. So we are now in the AT command, and if we look into the AT commands, there is an AT command for display the current network status. That is this one. And if we use this command, we should receive maybe first. Okay. I know what's wrong. This device terminal is not transferring the carriage return line feed. I have to close this one. That's why I select different serial device terminal. From 7 here, connect. We are in the same mode. We use that and sending carriage return line feed, and then there is this message. Yeah, we have that status. We have the 192, 178, 111, 158. That is our IP address. We have the network mask, the gateway. So this is the network status. So now I can configure with a lot of those AT commands. And also there is one command to exit. Exit was EIX. We can go out of the command mode. I have to check here what is the exit command. Hmm? Okay, it's must be no. Okay, we have to check the AT command set, and there will be a command to exit the command one, and then go back to the serial connection. Anyway, it's 105 minutes now. Maybe you have more questions.
Right now I don't have any further questions written down. Only this one for the chat at the end of the webinar.
Okay. Anybody? I think we.
I'm sorry, but it is one more question right now. Can there be more connection or serial to Ethernet?
Technically and theoretically, yes. Here by now, we implemented a single one-port serial to one Internet connection in this serial to Ethernet application. But you can because of the design of the module here, we have only one serial interface from the MCU here to the connectors. So, but of course, if you change the firmware, you can implement multiple TCP or UDP connections, access to the same serial interface if you like. But our current implementation is only one connection here and one connection from the Internet.
Okay, so I have no more questions right now. Hello, can you hear me?
Yes.
Okay, so we don't have any other questions. I don't know if you have anything else for us to share.
No, I think I hope I introduced Wiznet core technology, the chips and modules to our audience and to our hopefully customers. And I think we offer some free samples for the visitors of this webinar after applying the question. Maybe you can explain that more better.
Okay, so let me thank you for your presentation, and also thank you to all of you for your attention and for your time. At the end, I would like to remind you our short survey after this webinar, and if you provide us with your feedback, some of you will be a winner of modules from Wiznet. So let me thank you one more time, and wish you a nice day. And also all this presentation will be found at our webpage next week. So thank you one more time and have a nice day.
Yes, thanks very much.